is the curvature of space-time. And that statement is basically general relativity.
And the tension with Minkowski was he was a mathematician.
Yes.
So there's a tension between physics and mathematics. In fact, in your lecture about this equation, one of them, you say that Einstein is a better physicist than he gets credit for.
Yep. I know that's hard. It's a little bit of a joke there, right?
Yeah.
Because we all give Einstein a lot of credit, but then we also, partly based on fact, but partly to make ourselves feel better, tell ourselves a story about how later in life Einstein couldn't keep up. There were younger people doing quantum mechanics, quantum field theory, particle physics, and he was just unable to really philosophically get over his objections to them. And I think that story about the latter part is completely wrong, like almost 180 degrees wrong. I think that Einstein understood quantum mechanics as well as anyone, at least up to the 1930s. I think that his philosophical objections to it are correct, so he should actually have been taken much more seriously about that. And what he did, what he achieved in trying to think these problems through, is to really basically understand the idea of quantum entanglement, which is kind of important these days when it comes to understanding quantum mechanics. Now, it's true that in the 40s and 50s, he placed his efforts in hopes for unifying electricity and magnetism with gravity that didn't really work out very well. All of us, try things that don't work out. I don't hold that against him. But in terms of IQ points, in terms of trying to make clear things he could have, he was really good.
What does greatness look like for physicists, though? How difficult is it to take the leap from special relativity to general relativity? How difficult is it to imagine that, to consider space-time together, and to imagine that there's a curvature to this whole thing?
Yeah, that's a great question. I think that if you want to make a case for Einstein's greatness, which is not hard to do, there's two things to point out. One is in 1905, his famous miracle year, he writes 3 different papers on 3 wildly different subjects, all of which are the Big Bang, just for writing that one paper. Special relativity is one of them. Brownian motion is another one, which is just little vibrations of tiny little dust specks in the air. But who cares about that? What matters is it proves the existence of atoms. He explains Brownian motion by imagining their molecules in the air and writing their own. Brilliant. And then he basically starts to go along the road to quantum mechanics, which is a paper on, again, it's a boring label of photoelectric effect. What it really was is he invented photons. He showed that light should be thought of as particles as well as waves. And it all 3 of those very different things in one together. But the other thing that gets him genius there is, like you say, general relativity. So this takes 10 years, from 1905 to 1950. He wasn't only doing general relativity. He worked on other things too. He invented the refrigerator. He did various interesting things. And he wasn't even the only one working on the problem. There were other people who suggested relativistic theories as well. But he really applied himself to it, and I think as your question suggests, the solution was not a matter of turning it around. It was something fundamentally creative. In his own telling of the story, his greatest moment, his happiest moment, when he realized that the way that we use modern, in say in modern terms, if you were in a rocket ship, accelerating at 1 g, 1 acceleration to gravity, if the rocket ship was very tight, you wouldn't be able to know the difference between being in a rocket ship and being on the surface of the Earth. Gravity is sort of not detectable, or at least not distinguishable from acceleration. So number 1, that's a pretty clever thing. But number 2, if you or I had that thought, we would go, we're pretty clever. He reasons from there to say, okay, if gravity is not detectable, then it can't be like an ordinary force, right? The electromagnetic force is detectable. Charged particles around, positively charged particles and negatively charged particles respond differently to the electric field or the magnetic field. He realizes that what his thought experiment showed, or at least suggested, is that gravity isn't like that. Everything responds in the same way to gravity. How could that be the case?